Okay, I think we can move for our next talk. So Sai Venkatesh Pingali is going to give yours on talk on experiment setup and data acquisition. Thank you. Do you want to share our screen?
Do you see my screen
Yes, it's just not in presentation mode.
now?
Yes. No.
Okay. So I cannot see all of you. So if there is a question, even in the middle of my talk, you can stop me. Um, and thank you, Wellington. So I'm going to touch upon the experimental setup and data acquisition and reduction aspect of this workshop. So when you first, before you come, you you need to get some idea of what you want to study. What is the size of a particle? What is the shape of a particle? So let's, as an example, um, let's small angle scattering can only detect between 1 nanometer to 1 micrometer, or actually less than 1 micrometer. But um, you we could, in some cases, go slightly below 1 nanometer. We can, but usually that's the range. So let's assume we have a particle. Just for simplicity, I'm using some tangible figures. Um, so let's say we have a particle which is spherical, then the particle size we're going to get would be the radius. But you could also have non-spherical particles. Then you have two dimensions. One is the long dimension and the short. So you can get both these dimensions. You could get length or a radius of cross section if it's cylindrical. Now, this is only possible if the length is within the range that small angle scattering can access. You could have a rectangular cross section cylinder, a hollow cylinder. So there are many different shapes, and we need to have an estimate. We don't have to know the size. We just need to have an estimate so you can decide what Q range you would need so you are accessing the structural information you're interested in. The next thing would be concentration, as everybody before me has touched upon in some form of fashion. Um, Usually, we say more than 1 milligram per ml, between 1 to 5. If you have a much larger particle, you could go to lower than 1, but usually 1 to 5 milligram per ml. You could have distribution of sizes. Then you would need to have some idea of the range so that you know you're picking up the largest, and you probably need to have some estimate so you take enough signal at the lower for the lower size, because that would be signal to noise, would have the more effect from signal to noise. And usually we model it with different kinds of distributions in the fit. And then hierarchical, as I put some text in the chat. This is just a depiction. So let's say we are seeing the size, the shape of these big objects. One is triangular, one is square. But then you can also start to observe the order of these balls, how they're arranged within these big objects, and then the shape of a ball. So if that's your primary particle, then you get a structure factor for their ordering and then the size of the entire particle. So that's what we mean by hierarchical. There's multiple levels of structure, and you're picking up all of them. They're all convoluting with each other, and we need to tease apart that information. So having some idea of the length scales you would like to predict, uh, if it is a dilute system, then you would just go by 1 by R. That gives you the sort of the sweet spot of your Q, and then you want to expand on either side of that. Similarly, if you have some kind of a structure factor or a hierarchical system, which could be a combination of size and structure, you need to play with these to figure out, okay, what Q range will access the length scales that I am interested in to answer my scientific question. So now I get into the instrumentation. So we have an idea of how do we connect real space to the Q space, which is the reciprocal space. This is a schematic of our instrument. It's very much similar to most any SACS instrument. If you've already been to a SACS beamline, if you think of this as your monochromator, like the double reflection mirrors in X-rays, here we have more like a turbo that Luke had mentioned, has many panes that rotate and a specific speed of neutrons that go through each pane without being captured, make it through. That's how we select our wavelength. And we have a collimation section, which is a passive one. We just have guides with a aperture at some spot. The distance of the aperture from the sample sort of gives an idea of what is the angle of divergence of your incident beam. And then we have a detection system after the sample. We have a dual detector, one which sits close to the detector to capture higher scattering angles, one that can travel along the tank axis. So if you see, these are sort of the extreme. Let's say if we have the main detector at a close distance to the sample, then typically we have our source aperture, the virtual source aperture close. The other extreme is to have the virtual source aperture all the way to the beginning of the collimation system. That's more collimated beam. And then the detector goes all the way back. So just to give you an idea, think about this as a triangle. So this is the triangle that tells you about, that's the height of the detector that's accessing much larger scattering angles. As you move it all the way to the end of the tank, your detector is now accessing much smaller scattering angles. So as theta gets smaller, your Q gets smaller, so you get larger particle size. The next knob, once you have maximized your reduction in theta, is your wavelength, because Q is a function of wavelength and theta. And you start to increase your lambda, that way you decrease your theta. So we offer mostly these 5 configurations. We do customize configuration. It just causes more time for the user to get a reduction software, and all the accompanying background measurements, calibration will have to be done specifically. But otherwise, if we choose these are usually calibrated at the beginning of the cycle. The shortest is when this detector sits very close to the sample. Then we move the detector to the intermediate stage of this tank, then to the farthest with the most flux neutron wavelength. And then once we are at the end of the tank, we start to expand on the wavelength. This is a standard that we got from NIST. It's a porous silica sample. And this is data from the porous silica individually placed on absolute scale. They all fall right on each other. There's a slight effect due to wavelength at the peripheral of the wing detector. This is from the wing detector. And that's because the scattering angles are larger. There's different spread of the wavelength. I just expanded it just to show you how the data, what is this Q range of data we get from any one of these measurements. Typically, we take the green one when you have the most flux neutrons and the detector is at the farthest angle. And then we take a shorter measurement for either 12 or 18 angstroms to expand this data from here up. So in that case, we are only interested in the data on the main detector. For the higher wavelength, we don't use data from the wing detector, although we're measuring it. And we can take it for a shorter time then. This is just to touch upon the kind of example samples we have studied, or users come and study. So something like a globular protein, lipid nanodisk, where the lipids are masked. We only see the protein that coils around. The green is the vesicle, and then something which is more hierarchical. And just to give a feel of how do you make a decision. So let's say you already have some idea of what is your protein size, and you can do 1 by Q or 1 by R or some size, and you get a feel of where the Q sits. You can expect that the data will level off. Then by 0.007, then you can say, well, intermediate Q configuration should be enough because I don't need to go below. But in the case of even the nanolipids system, this system, it seems good here. But in the other two cases, you see that the data is just still climbing up, which means if you need that information, you need to go to much lower Q. In the case of the lipid vesicle, you can see it's sort of leveling off here. So in some cases, you could say, well, I could go till 15, I go to the end of the tank and use the 6 angstroms wavelength. That's a long configuration. I should be able to satisfy myself, unless you say, well, I want to know if it comes down or it goes up. Okay, you go one more, that's 12 angstroms, and then you say, oh, you know what, that's good enough. But in the case of plant cell wall, it's still going up, which is hierarchical. So we continue and we go to 18 angstroms. So there's some kind of, if it's your first time, there's some kind of learning. But if it is subsequent time, you can have some estimate of what to do. So at this point, we can also simulate these kind of measurements prior to coming, and we make some approximations, and then we figure out, okay, does this work? Does this not work? How much exposure? What concentration? What is the optimal Q range? Do we want more flux, or do we have to sacrifice some low Q to get much higher flux? Things like that. So I'm going to get out of this for a second and go in here. So we have something called the simulator that Volker had developed on an Excel that got now moved on to the EPIC system, which controls our data acquisition. And right now, it's still setting up. We have made it to start working on EPICs. We have to find a way how users can access this prior to coming. Right now, the access is only after coming, or if you're in remote, once your IPTS has kicked in. So it's not as well established for sharing with users, but that's our hope, that we'll try to get this out and users can test. So let's say you have a protein like lysozyme. That's about 15 kilodalton. We say it's about 15 angstroms at RG. That, if you say, is approximated to be a spherical sphere, and that will be about 20 angstroms radius. So I've chosen a sphere form factor, 20 angstroms. Then I said, well, I don't have D2O, so I'm going to run it in water, and the scattering length contrast for the protein and the solvent water, I put that. Then we go, what is the density of protein? It's about 1.35 gram per ml. And we may or may not know the molecular weight. In this case, I know because it's lysozyme, but for your unknown protein, you may or may not know. But you can know the concentration. So let's say you go at 1 mg per ml. You put it in water with 1 mm thickness, and you say 0% D2O. And I just put 500 because I want to show a lot of data points. That's what I fill as my sample. Now I go to configuration. I say, I don't know. I'm thinking I should go to 15 meters. I have to go all the way and get data till 0.003 inverse Q at minimum Q. And what you do is you have to go to zero guides, which means you're giving up some flux. Okay, and this is basically picked up from the configurations that are offered to you over here. So if you choose 15 meters, 6 angstroms, then it zero guides, it already populates all that. You don't need to worry about that. But what you may want to play with is how long to measure. 30 minutes, I'm saying. 30 minutes, that's your data. You're going to get raw data here. That's just the sample. and that's your background. Can you see that it's moving a bit here? And there's very small change there. But when you subtract, that's what you can see, that your data is sort of not as clean, but you still get some data. Okay, maybe I need 2 hours, so 120 minutes. And you do 120 minutes. And then you see it calculates, it says, oh, okay, I'm getting a little more points. Maybe it's okay. But then you say, well, that means I cannot study 4 samples, which I had thought of. So you need to then balance. So you say, okay, but if I can get access to D2O, then maybe I can do better. So I go here and I just need to play with these a bit. I have to make this 100. That's it. And then it does the calculation. It comes back here. And now at 120 points, you see how good your error bars are. And you're getting a huge amount of these oscillations. Well, I'm assuming they're spherical, right? But they wouldn't be spherical. They will be sort of a smear. And you can think, as Volker had mentioned, you would be getting more of like the envelope here. So let's go back to 30 minutes. And there you go. You still get reasonably good data here, right? So, and if you go here and play with just the data as you see the difference, how much of intensity is reduced by going to D2O because of you have reduced the incoherent scattering, which we didn't touch upon very clearly in our message, but workshop message, but that's very important for us to minimize hydrogens in the entire system, and solvent is one of the biggest contributor. Okay, so we can do this for many different shapes. I'm not going to touch upon all of that. You see there are many different options that they offer, and you can play, you can even put many different samples. So all of them show up over here at the same time. But I'm going to go back to my presentation now. Okay, so now that's for the simulator, and that's before you would have to know how much concentration would give you a reasonable data, as well as do you need to measure it in D2O or not. Now, this is very simple cases. If it becomes a little complicated, we need to figure out, do we have something that we can approximate for your system and then find a way to address that. Most cases we can. Okay, data acquisition now. That's the same EPIC system that I showed you right now, but I'll go back to that as I finish this. There are video tutorials. Initially, I thought I will just play the video tutorials, but I felt I'll lose flexibility if I don't go and show it live. But I've put these links because in case you do go back to these talks, you should be able to re-see these video tutorials. So a quick intro before I go to the live demonstration is we always, as we invoke this window that shows the main controls, to invoke it, you need to go, as you open this terminal, you need to click on the home button. As you click on the home button, all this shows up, and this SANS queues plan, which is currently only for staff because it's still in the development stage, is what I was showing you till now when I clicked on that. Okay, and the other important ones for user is this dashboard here, and that shows up. And the other one is the panel scan that's over here. Now these two are most of what a user would use a lot. They first come up here. They will need to click on the dashboard and then click on the panel scan. There is one other window that is important for you, that is to go through the applications. Then you, under applications menu, you go to scans and then scan monitor. And I'm going to talk about the panel scan, which is a bit more elaborate. Then I go to the dashboard and the scan monitor. So the panel scan will look like this. It has 6 tabs. the first tab is really to create the configurations. We can create customized configurations, but as I mentioned, a lot of the calibration and all has to be then done during your beam time. If we can avoid doing that, that'll be much more useful for you. And what we normally calibrate during a calibration time is these, which I've already touched upon. First, you very close to the sample, intermediate, farthest from the sample, and then we turn the wavelength knobs. Usually, what I suggest users to have a memory of is whether they use 6 angstroms, 12 angstroms, they use a mixture of them. Sometimes if we reduce the sample aperture, we could increase. Maybe we use one guide. So there are some variations that can be done. So it's good to have some estimate of all these different parameters that you have used, especially sample environment. Okay. Thought I didn't jump. Okay. Then once the local contact has helped establish what configurations you're going to use and save that for your IPTS, then we can select your IPTS, and then this setup here will only have those configurations. You will not have all the configurations that you may not even need to know about. But then you have to select whether you want to measure only scattering, only transmission, whether you want to measure both of them together, because we have a semi-transparent beam trap, and it allows you to get transmission as you're getting scattering, useful for time resolved or kinetic studies. But in some cases, you're not using 6 angstroms, then you have to do it separate. In fact, even if you select that option, it will be done separately. And we have the option of selecting 4 setups to run, but because of the dual detector system, we normally use 1, sometimes 2. Unless you have a variety of systems and you have some set of configurations for one set of system and some other for the other, then you just select all of them, keep them available for you. That's a possibility. Now, the other is a default exposure time that gets populated down the tab, and you can set that up here. But you can also, you have a chance to, again, edit them if some specific samples are not in the default exposure time. You can also choose which one. Usually, we have been doing time. Little more experienced people can choose the other ones. But if you're new to scattering per se, it's better to just go with time first and then get used to it. The others can cause you trouble. The next tab is sample environment, and it lists all the different sample environments. You can Peltier controlling system. We have 2 different Peltier, one that controls the robotic arm sample area, sample holder. The other is a multi-stage Peltier system that allows you to control temperature of each position separately for banjo setup. There's a regular water bath. Some of these options are not available for us. It's more on the GP SANS, but because we try to keep similar setup, some of these things show up for us too. The tumbler, yes, I think this is the only one as of now. This also we can use. We also have the option of choosing something that you want to run after a measurement or just before measurement, and then go into measurement. If you want to put some equilibration time, we also have an HPLC. Then we go to load samples. 4th one is the load samples. Here, we have a lot of options for load samples, and mainly what we need is what sample environment, so you know how many positions are available, and then each position, what sample is currently stored. It is good to have more information of each sample as we go about. The metadata get populated with this. It's easy to go back and check what you have measured and whether it's correct or wrong. And also, as the auto reduction kicks in, it can associate a background for a subset of samples. In those cases, we are expecting that the background has to be run first and then all those samples. then the next background, all the samples, something like that. You can also run all the backgrounds, and then you can choose which set of subsets of sample need which background. So I'm just expanding that to show you there's a sample changer that allows us to use the robotic arm, the banjo 15 position, the rectangular cell 18, the Peltier, which is 8 position. We have a titanium cell 9 position. So that all these comes under the sample changer. And the actual sample is holder is selected by the local contact, so that will automatically get populated here. And then we do need to put a title, the background. There are many other electives that's good to populate if you want to keep all this in your metadata. And then you come to the 5th tab. The 5th tab only touches upon the time for sample. This is populated from that default time in the 2nd tab, populated for every sample, scattering exposures. And one thing I forgot to mention is in the 2nd tab, when we select transmission, that we want transmission, it will allow you to enter the exposure time for transmission. So this is not the time for the transmission exposure time if it's done separately. This is only for the scattering. And that's what I mentioned here. Yeah, okay. So then, so if we change whatever you change here, that then gets moved to the next tab, that's 6. But if you don't change, it just uses the default exposure. Now, all the other tabs have only a limited amount of editing, whereas this last tab uses all the information from the 1st to 6th, 1st to 5th tab, compiles them as one whole table. Here, there's a chance to edit a lot more. You can edit exposure time, you can edit temperature for sample environment, you can edit the order in which these should be run. Each row is self-sufficient with exposure, with configuration, exposure, sample position, the sample environment. So there is no connection between the 1st to the 2nd. You can move them and it will still be correct. Okay, and then that's it. So that's how we submit our, okay. If you click over here, that's when you submit it. Now, once you've submitted, you want to observe what's happening. That's when you go to the dashboard. The dashboard looks like this. It shows you the detector, the 2 detectors, the count rates, and this is the position where the run and the scan information is shown. Right now in this, it says that they're idle. These 2 boxes, which are orange, if you have submitted the panel scan, then the scan would be green. That means something is running, but the run may not be green unless an exposure is taken. If motors are moving, then the run status would be orange. So both needs to be green to tell you that yes, we are running and we are measuring at the same time. You could also control and do some diagnostic runs from here if you have not initiated the panel scan. And this is where some of the motors, or the motors that's more relevant for users, are shown. And some of these motors also can show you if they are in a error state. So if a user sees a red or an orange, well, red, that means there's an error. Orange could just mean that it's during motion. The other is the scan monitor. We get that from the applications, and then scan and scan monitor. And since I got this not when the reactor was on, I don't have the 3 different buttons that show up, but there are 2 buttons that allow you to move a command, reorder these commands, move it up and down. And there's one more to abort. sorry, there's one to move it up and down, but there's also one, to move it up and down and abort. The active command that is not is locked and you cannot move it up and down, but you can skip because each row is a collection of commands. You can skip to the next command within that macro, or you can abort the whole macro. Usually, I recommend users to just skip to the next command. Aborting it fully would mean it may not finish it safely to get to the next step. Okay, I have another 8 minutes or less. Okay, so now we have taken data. We have the data. How do we reduce? We have Jupyter scripts. We have scripts available for users in the Jupyter Notebook environment. And this box you see here basically has all the information that the user needs to fill in. If they ran multiple samples, they can list all of them. They just need to list the appropriate information. The next set of windows give more information. So I've expanded that list. First thing we need to know is what configuration you're reducing. Is it 1 or 2 configurations? This is for a 1 configuration script, but we do have options for 2 also. And so you choose which of these configurations you chose. It can be modified by us if you use custom designed configurations. You can list multiple samples, their appropriate thicknesses if they are different. If they are the same, you just leave 1 and it'll automatically populate all of them with that same thickness. Then you list samples in the same order. If you have 2 runs that associate with the same sample, then you just list them within the same code, like over here, instead of individually and with a comma outside. You put the comma inside, but the comma here is the comma outside. Now, if you took a scattering and transmission measurement, which was simultaneous, then you just leave this empty. It'll automatically know that it needs to use this even for transmission. If you have a separate scattering and transmission measurement, then you will need to populate them appropriately here too. Now, background, I think the background comes here. So background, scattering and transmission, the same thing. If it is separate, then you need to have each populated. Otherwise, you can leave it as empty. Now, background also could be just a single one. Then it'll copy that same background for every sample reduction. Many times a user may reduce their data with empty cell or with a solvent that's common for all their samples. Or you may have subsets of solvents that you want to go with some subset. So then a good way would be to list all of the same solvent. So you put that, if you have listed 5 of them, you multiply this into 5. Like, I don't need to get into detail, but something like that can be done. And beam center, empty trans, these are the initial measurements that we take for every user. If it's not populated, then the script actually uses the calibration experiments, beam center and empty trans for this configuration. But it's better to use the one that you ran because that will be the most up-to-date one. And the start and end index is more for us to be able to run or reduce a subset of these list of samples you put. If you have, let's say 10, and you now want to reduce from 5th to 7th, you just put 5 here and 7. So you don't need to delete anything. You can keep the list. You just play with the start and end, and it'll reduce a subset of those, the entire list. And then, of course, you need to put an IPTS number so it knows where to go and save your output. And usually I suggest users to put a 3-letter code or any small name that will be their output folder file name. Everything else in the script doesn't need to be touched, and then just execute. So there are a few more information about how you can get access to the data once you've reduced it. So I made a small diagram to give an idea for users. First of all, you're going to use Jupyter Notebook to do reduction. And usually there is a template script that we offer. The local contact will give it to you. You can copy that from, or we send it as a copy, either way. And then what you do is you prepare the script that matches your experiment. And that's the first cell of the entire script. And then you will access the script. When you run the script, the script will access raw data within the cluster, right? And on the side, then you again go and get an FTP software, so you can transfer data to your computer and log into that. When you're logging into this cluster. This is usually sitting outside the cluster, and then you log into the cluster. That once you log into the cluster, now you have access to the reduced data, and you use that reduced data to transfer it to your home computer, and then you can do all kinds of plotting and data analysis outside with any software you want. That's it. Thank you. Any questions? Hello?
Hello.
There's no questions yet.
Got you here.
I'm not sure if I was not sure if I was still online. Okay.
Yes, people can ask questions tomorrow as well at the breakout sessions. A lot of this will be recovered there too.